In accompanying this webinar, we do have a HVAC course running. If you want to find out any more information, please visit imeche.org/training calendar, or click on the QR code on this screen. This screen will be repeated at the end of the session for those of you who haven't had a chance to look at it, or those of you who have joined since we looked at this screen. To save time, I will now hand over to Alex to present the webinar.
Excellent, thank you, Rob. So, hello everyone, my name is Alex Zacheshigriva, and I am one of the trainers who work with IMechE Learning and Development Department delivering the training. My areas of expertise are within the thermofluids section, HVAC, and some of the piping design courses. And for this webinar, we will try to cover quite an important and interesting topic of psychrometrics. What we would hope to get across is what the psychrometrics are, why they're important, in general, how to work with them, how to work with a psychrometric chart or a software version of a psychrometric chart, and how do you apply specifically to heating, ventilation, air conditioning needs. Now, you may be coming from different areas of heating, ventilation, air conditioning. Maybe you work for industrial type of applications, maybe domestic, maybe commercial property, and depending also where your projects are in terms of the geography, you may have a slightly different view on this and slightly different needs, but hopefully this will be useful to all of you, and it will cover both the basics and the physics behind it, but also specific application to things like heating, cooling, dehumidification, and why this is important. In terms of the agenda for today, we will first of all briefly talk about what is psychrometrics. We'll talk about what is air and what is water vapor in it and why is it important. And then we'll cover a number of things. We'll talk about the psychrometric chart. We'll be going back and forth psychrometric chart and then looking at various things like the dew point and saturation, dry and wet bulb temperatures, absolute versus relative humidity, enthalpy, i.e. the energy of the moist air. And we will, at the end, look at a few psychrometric processes. So we'll look at a realistic HVAC layout, plotted over a psychrometric chart where you can see various properties and you can see how we can use them to calculate cooling loads and heating loads and states of air in different parts of our process. And we'll also cover a bit about the sensible and latent heat, the difference between them, the importance, and how you can integrate that into your design calculations. So let's get started. First of all, psychrometrics, what is it? A definition, or one of the definitions from a textbook, is that it's the science that involves the properties of moist air, a mixture of dry air and water vapor, and the processes, which could be meteorological, air conditioning, dry, humidification, dehumidification, in which the temperature and or the water vapor content of the mixture are changed. Psychrometrics can come in a lot of different things. People who work with weather from Met Office and places like that, they will know a lot about it. Their view and approach to it will be slightly different to HVAC. They will look at the processes like cloud formations that go on in the environment. They have a different scale altogether. We will be specifically looking at it from the interest from point of view of air conditioning for dwellings and also commercial and industrial properties alike. In terms of the origin of the word, just briefly, so a psychrometer was basically what now would be called a wet bulb thermometer. We'll discuss what a wet bulb thermometer is in a minute. It was invented in 1825 by a German scientist, Ernst Ferdinand August, and he named it from psychro, Latin for cold, and meter, Latin for measure, so a way of measuring coldness. That was his take on it, and that's where the word comes from, and then now it goes into psychrometrics. Okay. So first of all, what is air made of? We have a ventilation system. By its nature, it's moving air around, it's heating the air up, it's cooling it down. But what is actually air made of? Well, dry air itself is made of a few gases, nitrogen mostly, some oxygen, about 20%, and about 2% others. And here's a split down further if you're interested. There's CO2, there's nitrogen, and so on. The thing about them, as far as we're considered from point of view of designing ventilation systems, all those gases are perfectly mixed, and we can deal with them as a mixture. We can work out their properties once in terms of things like specific heat capacities and densities, and we don't really need to be recalculating the state because the percentages don't change and the behavior can be modeled as a perfect mixture. And for all intents and purposes, if we only dealt with dry air, we wouldn't need to worry about what exactly is it made up of. However, the real air in our atmosphere, in pretty much in all of our installations, unless you have some sort of specific very complex dry room environment, will be a mixture of dry air and water vapor that is there. If you were now sitting in the room without any water vapor in it, you would actually feel very, very uncomfortable. Your skin will be very dry, your eyes would be very dry, your mouth and so on. It would be very uncomfortable for you indeed. So yeah, anywhere that you are, there will be water vapor mixed in again. Now, in terms of how much of it there is, well, let's have a quick look. Here's a chart that shows an example of a few different conditions. So something like 10 degrees C and the relative humidity. And by the way, I will explain properly what relative humidity is later on. Hopefully you get a general idea of what it is. About 10%, a relative humidity of 60%. Here's the ratio in terms of the weight of dry air versus the weight of the water inside the mixture. And then as you can see, if we increase the temperature and we increase the relative humidity, it starts to be a little bit more. However, as you hopefully can see on this graph, it's a tiny slither. And you could say, well, all right, that's interesting. So there's a tiny amount of water mixed into the air, but however, it's such a small amount. Why do I need to care? Can I not just ignore it, or can I not just put a factor on my calculations and keep it static all the way through? Well, no, you cannot, and there's a good reason for that. The reason is, why is water vapor important? It's the latent heat of evaporation. That's what's really important. So if we look at the water vapor and the state of it, then if we look at water, to warm up vapor, sorry, to warm up a kilogram of air by 1 degree would take us 1 kilojoule of energy. However, to evaporate 1 kilogram of water would take us 2,450 kilojoules. So it's a lot more energy, as you can see. So the point is, it's not so much that water itself has a very high specific heat capacity, although yes, it does have higher heat capacity than air. Given that there's so little of it by comparison, it could almost be neglected. Why it cannot be neglected is because when it changes state from liquid to vapor, or the other way around, from vapor it condenses back into liquid, that has a huge impact on energy and of the whole mixture, and that's where it becomes important. I'll give you two examples that highlight the difference. So the first one we'll look at is, what if we're cooling some air but there's no condensation of vapor, i.e. the vapor will not change its state, it will remain as in its gaseous form, it will not condense into a liquid. So if we were to ignore the moisture and we say we don't want to know what the relative humidities are, we just know it's air 30 degrees cooling down to 20 degrees, that's the calculation you would do. The heating required, so the cooling required, the amount of cooling load would be Cp times the difference in temperatures. And that would give us that we need 10.06 kilojoules per kilogram of air. Now, if we do account for the moisture and we work out using enthalpies, again, we'll cover what the enthalpies are a bit later, but that's basically the energy content. Then we'll get 10.3. So the error is about 2%. Very small error. Again, you'd be excused to ignore it. So if there was no change of state, you would be fine. Now let's look at another example. Oh, apologies. Now in this case, we do have condensation. We're going to be cooling air from 35 degrees and relative humidity of 70 to 15 degrees, relative humidity of 70. Now, the relative humidity is not changing. However, the absolute amount of moisture will change. And we'll describe that in a minute as well. And you'll see it very clearly on the chart. But just believe me that we will be condensing some of the vapor into droplets of water. So if we were to ignore the humidity content and use the same approach as before, we would say that we require a cooling load of 20.12 kilojoules for every kilogram of air. Now, if we do account for the moisture and we use the enthalpies that we can read from a psychrometric chart, we would say that we need 67 kilojoules per kilogram. So the error would be about 70%, or basically will be out by about a factor of 3. it's a huge error, and you would be nowhere near close to correct answer if you were to ignore that. So that is where it's important. I think as well, why I like to highlight this is that if you look at the conditions, 35, and that's quite humid air, somewhere in a tropical region, Singapore, something like that, this is completely normal outside temperature, and people working there and designing HVAC systems will be more than used to it. In the United Kingdom, often people don't expect temperatures as high as this, or they don't design for that, and they don't think. And a lot of the time, we size our systems for heating, and in that case, ranges of 10, 20, 10 degrees are maybe more common. And you do find people who quite often did just use the simple equation without worrying about the moisture content, and their error wasn't very big. But it's only as good as you stay in this region where there's either very little moisture or it doesn't change state. So let's continue and look at the importance of the water vapor within the mixture now that we convinced ourselves that we have to consider it. What you basically need to look at is a chart like this one, where this is the properties of water vapor. They are kind of irrelevant of the air around them. That's just the vapor itself. And what that gives us is a saturation pressure, or the pressure at which it will change depending on the temperature. It would change to a it would change from liquid to vapor state, to gas state. So what we got here is, on this side we have a liquid region, on this side we have a vapor region, and we also have a solid ice. Now that doesn't tend to come up into the HVAC design as much. The solid ice, we don't tend to freeze our air completely, so you need to worry about it a bit less. But that's the important thing. And the important thing is really the graph that shows us the pressure at which it will be changing phase. And that's the pressure. So as you would expect at 100 degrees at the sea level, that would be about 100,000 pascals roughly. That's when you will have it boiling. So all of your liquid will be boiling into, if it was that hot. But the important thing is, you say, well, my systems don't work anywhere near 100 degrees. That won't be happening. The important thing is, wherever you are, be that 10 degrees, 20, 30, 40, or so on, there will be a certain pressure at which water would be changing from a liquid into a vapor. And the idea is, if you have any space, whether it's filled with air or not, actually doesn't matter. If you just have an enclosure, if you imagine a volume of space, and you put some liquid water at the bottom of it, what will happen is, depending on the temperature, some of the molecules will start evaporating. They will start changing phase. They will start filling up that space that you created with some vapor, water vapor in it. And as more of it evaporates, they will start creating a pressure inside this volume that we've created. And once the pressure reaches the saturated pressure at the temperature that we are at, that will get into equilibrium. So some molecules will be evaporating, but others will be condensing. Overall, the amount of molecules in the vapor state will stay static at that point. And that will change either if we change the pressure inside the volume, or if we change the temperature. So that's the important thing. So basically what that means is that for any temperature that you have, there will be a certain amount of water vapor that is natural, so to speak, that wants to evaporate to get into equilibrium, and it wants to reach this partial pressure of water vapor inside this volume to be equivalent to saturation. And once that's reached, we're in equilibrium, and nothing is evaporating or condensing. Or to be more accurate, the amount evaporating and condensing matches each other, so there's no change in overall balance. Okay, now let's try to bring together a number of things we discussed before. Temperature, wet bulb temperature, enthalpy, the partial pressure of water and other things, and absolute and relative humidities, and bring them all onto one chart. Now that would be nice, wouldn't it? And that's exactly what a psychrometric chart is. This is a very typical layout. This one is out of SIBS. You may have seen it. You may have seen slightly different layouts. There's one where it's shown as a square. It works exactly the same way. It's just the ways of drawing it are different. Now what we'll do is I'll quickly go through what this chart does, and then we'll move on talking about individual properties of it, and then we'll start plotting some things on it as well. So what this chart does, it brings together a number of different properties of wet air, or humid air, or moist air, if you wish. And the great thing about it is that it's a two-dimensional chart. Therefore, if you know any two properties, you can find where those two things cross. You can put a point on a chart, and then you can read all the other properties by just following the correct axis to the correct axis to read it. And you can find all the other properties at this point. So any two properties fix your position. That's what's really great about it. That's why it's so good that it's just 2-dimensional, not 3-dimensional or 4, and so on. So that makes it so nice to use. Let's first of all look quickly at what we've got. On the horizontal axis is our dry bulb temperature. That's basically what we would refer as temperature. That's what you would measure with a normal thermometer for your air. So that's temperature. Okay, in this case, it's in degrees Celsius. On the vertical axis, we have a moisture content, and that's an absolute amount, and it's measured as kilograms of water vapor being carried by the air divided by the mass of the dry air. So that gives you the how many grams of moisture we're carrying per kilogram. And the reason it's done as grams per kilogram is because, as you can see, it already has 0 with the 0. If we did kilograms per kilograms, there would be just loads of zeros to work with. So that's why we do it in grams per kilogram. But that's basically an absolute amount of moisture for every volume of air that you have, say, cubic meter or 10 cubic meters or whatever you're working with, or per mass of air. Then we have the other thing that we have is the wet bulb temperature. It's this curve over here. If you follow this curve, you can see we have temperature -5, 0, 5, 10, 15, 20, 25. This is wet bulb temperature. So what is a wet bulb temperature? Why is it important? What is actually physically? Just a quick one. Basically, it's measured using something like this. There's different type of mechanisms you can use. This is the original one called a wet bulb thermometer. So the idea is you have two thermometers. One is the normal one with a normal bulb, and the other one has a water-soaked wick on it. And then what you do is you fix them to a handle and you spin it around and you rotate it around. That creates a steady movement of air around the wick, or well, the wick is moving through the air. What does that do? Well, what it does is that the dry bulb just measures temperature of the air. The fact that you're moving through the air makes no difference. But the one where it's evaporating because of the movement, we get a cooling effect. Remember what we said, when you evaporate some liquid, that absorbs a lot of energy. So therefore, it will have a cooling effect on the bulb that's measuring the temperature. The more evaporation we get, the higher the cooling effect. So what it means is that if this is very dry air that very easily evaporates, there's very little moisture in the air. Therefore, we're far away from the saturated pressure, and therefore it's really easy for the liquid to evaporate into it. We'll have a lot of cooling, and I would expect that my wet bulb temperature would be much lower than my dry bulb temperature. That would indicate very dry air. On the other hand, if the air is saturated, the amount of vapor in it already is high enough that it provides a partial pressure of vapor that is equivalent to the saturated at this temperature, then there will be no evaporation at all, because no matter how hard they spin it, I mean, some of it may just fly out kinetically, but there will be no actual evaporation. Therefore, there will be no cooling effect. Then my wet bulb temperature should equal my dry bulb temperature, right? And the way it's shown says those diagonal lines on the line. But let's just go back to the chart for a second and have a look. See where we have 0 degrees dry and 0 degrees wet. That is where there's no more moisture can be absorbed because it's already saturated air. 5 and 5, 10 and 10, right? 15 and 15. So this top line, the curve, that actually shows me a relative humidity of 100% or saturated air. It means it cannot take any more moisture. And if you try to sort of go this way on the graph, i.e. cool it down further, the moisture will start to condense. And we'll talk about it when we talk about the cooling coil. But that basically is the point. It's the dew point. That's where the point where the water vapor will be turning into liquid. Okay, so that's and on the other hand, if we look at any other place, if I stay, for example, here where I'm pointing now, then my dry bulb temperature can be read from the axis at the bottom. That's 10 degrees. But if I travel across, my wet bulb temperature in this case is 6 degrees. So as you see, it's lower than my dry bulb, and that will be equivalent to a certain amount of humidity. If I want to measure absolute humidity, I can read directly across, and I know how many grams per kilogram of air I have in absolute humidity. And if I'm interested, what does that mean in percentage of relative humidity? That's those curved lines coming from above. I think I have a better slide that shows it. No, okay, sorry. So it's those curves that come down. There's 20% humidity, 30%, 40, 50, 60, 70, 80, 90, and as I say, this is the 100% humidity. As you can see, when the air is quite cold, then all the lines are pretty close together because the capacity of air to carry moisture is not particularly great. The hotter you get, the more moisture the air can carry, and therefore the lines become far apart because there's actually a law of moisture that you need to add to move 10 or 15% up that scale. So that's the relative humidity. Okay, and then another thing to highlight quickly while we're on it is the enthalpy. That's the energy content. The scale looks a little bit maybe strange, but the way it's easy to use is if you have a ruler on the paper chart, and wherever you have your 2 points where you cross, you put it there, and you put the ruler across at the correct angle, so you're reading off the scale. And the value that you're reading here is kilojoules per kilogram. So it's energy content per kilogram of air mixture. And that tells you the accurate energy content. That includes energy stored in the dry air as well as energy stored in the moisture. Okay, so relative humidity and dew point, why are those important? Well, the reason the relative humidity is important is because that actually gives you a good feel for what will be happening to some liquid or will be happening to some moisture that's already in the air. So if the relative humidity is low, it shows that there's a lot of capacity for this air to be taking up more moisture. So more moisture can evaporate and change from liquid into a vapor, and therefore we can dry things out that way. On the other hand, if the relative humidity is high, close to 100, then it means that it cannot pick up that much moisture, so it's not going to be very good at drying, but also there's a risk of condensation, and also just things will generally feel quite, heavy and mucky because of that. From the personal point of view, from human point of view, we'll talk about it a bit later, but basically we like relative humidity not too high, not too low. If it's very high, then we feel very kind of stodgy around us, and whenever we sweat, it doesn't actually evaporate from us. And when it's very low, then as I said before, it will feel very dryness, our eyes dry up, so we don't feel very nice either. So you want somewhere in between. This I think is a very good little diagram because it just shows you how relative humidity can change very quickly as the temperature changes, although the content of moisture may stay the same or stay close to the same. So let's look at this hypothetical house. It's cold outside, -20, relative humidity of 90 degrees, but bear in mind at -20, air can carry very, very little moisture. So 90 degrees doesn't actually mean it's very wet. It just means it has low capacity to start with. That air enters into the roof space, for example, loft space. Now, the loft space is not heated, and there's a thick insulation. So although it gets some heating from the house, it still is at -10 degrees. But you can see the relative humidity plummets to 36 degrees because as we warm up from -20 to -10, the ability of us to carry moisture is much higher. So that would create a really good drying effect, and our roof will be able to dry out and release moisture, and it actually will not be soggy and damp. It will be drying through that, and then it can come out and leave. On the other hand, let's look at what happens inside the house. Inside the house, we're heating it up, so it's 21 degrees. Relative humidity is nearly 50%, so quite nice and comfortable for people. As you go towards the warmer surfaces at the top of the ceiling, because the heat rises, relative humidity is lower. If you go to the colder places, like your floor, relative humidity is higher there. If we look at some corner where it's particularly cold because of cold bridge, and this corner is particularly cold, we actually may have dew point, i.e. the temperature 5 degrees, and at that point, the water actually starts to condense. So then that's where you get the condensation and maybe mold and things like that going. Another example here, typically a window, because windows are never as well insulated as the walls. Again, they're quite cold. That's where you get the condensation. So when you get condensation in your room, yeah, it makes sense. It means that you have enough moisture to start with in the room as a whole, but you have a specific point which is very cold, the surface. Typically, it's a window or somewhere else where there's a cold bridge, and that's where you will have the condensation. There could be various different answers to that, kind of how do you resolve this, what do you do with it, but at first we need to understand what is actually going on. Another interesting point here shown is that, let's say we have an extractor fan that takes this warm, moist air and pumps it out. Now, if inside this duct itself, it cools down because of the space, the loft that goes through is being cold, and the walls of it lower down to say 5 degrees C, again, it's a dew point, and at that point we start to get condensation inside the duct, and then we get water and maybe corrosion and a growth of algae and stuff like that. So again, that's where you have to be careful that, sometimes people think, well, it's perfectly fine here, it's 50% relative humidity, I'm just throwing it out through a duct. Depending on its length and its shape, you may risk that you'll have condensation within it. Okay, let's move here. And then they say specific enthalpy, it's this on this side of the chart, shown like that. And the lines, they're not at the same angle as wet bulb, but they're very close. So when you have both of them shown at the same time, it's easy to be confused. With electronic versions like this one, the good thing is I can choose which axis to switch on and off, so I can put them on and off as I need. In this case, I've highlighted the enthalpy ones, so you can see how the enthalpy moves. And as I say, the total enthalpy in kilojoules per kilogram, made up of two. So it's made up of the enthalpy of dry air plus the enthalpy of water vapor, and that itself is made from two things. It's the change that you have just in terms of heating up the vapor itself absorbs some heat, but the really important thing is this one here. See, that's the latent heat for evaporation. So that's evaporating any amount of liquid into vapor, absorbs a lot of energy. Okay, so then let's look at some basic processes on our psychrometric chart. So remember, this is dry bulb temperature, this is absolute humidity. The relative humidity lines come like that across, and then this is our dew point, and we can't have any vapor on the other side. Well, we will have condensation once we go on the other side of it. So what we have is we can have a few things. If we are moving across from point O origin to A, then we're just heating up our air. So we're increasing its temperature, but we're not adding in. See, the absolute humidity stays the same. So we're not adding or subtracting any moisture. Therefore, we're just heating it up. That's called sensible heat. If we're cooling across the straight line like that horizontally, that's called sensible cooling. So that's cooling without condensation. We're just cooling it down. On the other hand, if we go vertically up, temperature stays the same, but we are adding more moisture. So we're increasing the moisture content. That will be humidification, and that will be latent heat. So as you can notice, if I go back to this chart, if you pick a point and you keep the temperature the same and you travel vertically upwards, and then you read across, you'll see that your enthalpy has increased a lot, i.e. you've added a lot of energy to your mixture, although the temperature, dry bulb temperature, stays the same. Why did you add it? Well, because you've added moisture, because you've evaporated some water and that absorbed energy. And then the same, if you go vertically down, that's pure dehumidification without any cooling or without any heat gain. So we have purely latent cooling, so no temperature change in this case. So those are the four basic processes that you have. Then you can have others. So one very important one is if you are moving up or down a constant enthalpy line. So that means that the energy content of the mixture stays the same, but we are changing temperature and we're changing the moisture content at the same time and at a particular ratio. And that would be adiabatic process. Adiabatic means no heat added or subtracted. So the amount of, in this case, if we move from O to E, for example, we are cooling, but at the same time, we're increasing the moisture content. So the amount of sensible cooling that we have provided is offset by the amount of sensible latent heating because of it. So the total energy stays the same. And then this could be a adiabatic heating, whereby by absorbing the energy as the moisture is condensing, that adds to the temperature. So you can travel in that direction. And then you can have other processes that are somewhere in between, basically. So that will be not purely heating and not purely cooling, but something in between. And they can also be described sometimes by the sensible heat ratio. And we'll talk about that later near the end of the webinar. Okay. So in terms of human comfort, what's important to us is, say, typically you would look at temperature between 18 and 23 and relative humidity between 30 and 70. That's that region around here on the graph. Now, different things will give you different, depends on many factors: the outside temperature, the activity, clothing, the radiant heat. So like if you have a radiator close to you pumping out heat, air movement, the velocity of it, the expectations of people, a lot of things depend. So realistically, the envelope could be significantly larger depending on the situation. If you want more details on the human comfort and so humidities and temperatures, then I would recommend you look at SIPS KS6 and ASHRAE standard 55 as a few good points of reference. So what does the HVAC have to do? What are the loads? Well, first of all, we need to think about the outdoor air, because that very often is what we have to deal with. We take air from the outdoors, we put them inside, we maybe mix it together. This is a graph of most common conditions, so temperature and humidity, or relative humidity, or whatever, in London, UK. So this, assuming there's a lot of UK audience on this webinar. So as you can see, the outside tends to be quite cool. It is quite high relative humidity. However, it's pretty low absolute humidity when we're here. So as soon as you start heating it up, just sensible heating, your relative humidity drops right down. So we don't have to worry. Say somewhere like Singapore would be clustered around here. That's a much higher total content of moisture in the air, and that would make a big difference. Okay. This graph, again, so take that with a pinch of salt, but it shows quite well, depending on what the outdoor air is like. This is from SIBS. It basically says if you're here, then you have to heat and humidify. If you're here, you only heat it. I would argue that here mostly you just heat it as well, given that people in any place that you are working with will add moisture through perspiration themselves. And then over here you have to cool and dehumidify. And in this small slider you can just cool without needing to humidify the air. Okay, so let's look a bit more in detail at that. So first of all, let's look at the winter cycle. Let's say we have a room that we are keeping at 18 degrees C and relative humidity of 45. So it's nice, comfortable for people. And the way we're doing it, we have fresh air being taken in from the outside. And the fresh air, so I thought I would say the parameters of it, but it's fine. I'll show in a minute. Basically, it's a cold air outside. We bring it in, we put it through a preheater. So we warm it up a bit. Then we mix it with some recirculated air. Mixed air, the mixed air altogether then goes through another heater, gets even warmer. Then we can add a little bit of moisture in a humidifier, if that's what we want to do. In this case, we do. And then we supply it into the room. That mixes with the air in the room. It's warmer than the air in the room, therefore it increases the temperature, it adds heat, and also it's a little bit wetter, so it adds some moisture to it as well, increasing its absolute humidity of the air here. And then we extract some of that and we return this air. Some of it gets exhausted, the rest gets recirculated, and that's our cycle. Okay, so hopefully that makes sense. Let's have a quick look. So how would that look on a psychrometric chart? Well, what we will do, yes, and by the way, I just point out, so fresh air 1 over here, the conditions are 5 degrees and relative humidity of 70. And as you can see, I've plotted here the values that I'm particularly interested in. So I've got dry bulb temperature, relative humidity, enthalpy, and the absolute humidity in grams per kilogram. And this is the mass flow rates. And I've kept them easy. I kept them in there's once or 0.5 kilograms. So 50% recirculation, 50% fresh air uptake. Yeah, so point 1, I can plot here 5 degrees and 70. Once I've plotted from the software, from the chart, you can read the rest of the values. So I can read them directly off the chart. So from 1 to 2, it's sensible heating. I'm just increasing the temperature of the air. I'm not adding or subtracting any moisture. So my relative humidity will change, as you can see. It goes from 70 to 50, but my absolute humidity stays the same. The amount of moisture stays the same, just my temperature increases. What happens then is I'm mixing. So I know my air at 0.2, I know my air at 0.3, because that's this 18 degrees and relative humidity of 45. That's my air in the room. So I know that. Okay. When you're mixing two streams on a psychrometric chart, what you can do is you plot the two conditions, in our case, condition 2 and condition 3, and you draw a straight line between them. And the mixture, the final mixture, will be somewhere on this. And how far it will be towards 0.3 or 0.2 depends on the mass ratios. So in this case, we are mixing half and half, so half a kilogram and half a kilogram to get 1 kilogram per second flow rate. So therefore, we will be exactly in the middle, and we can work out the same distance from both and plot it there. If it was some other value, you could work it out from there. So that's going to be quite easily done from the ratios of the mass flow rate that you have. So that way I can work out the conditions at 0.4, which is my mixed air condition. I can pick them up from the chart, and I can read that, in fact, I'll have 13.9 degrees, 49% relative humidity, and that is equivalent to that enthalpy and that amount of moisture. In terms of moisture, you can see what happens if you take the value, the absolute value for the fresh air coming in, and the absolute humidity for the mixed return air. the recirculated air. And if you look where the halfway point is, because I'm mixing 50-50, that's what would happen. Basically, we'll be averaging the value, and that's where 4.8 comes from as well. So you could work it out that way. And what we'll do then is we'll heat it up. So again, sensible heating, we're not adding any moisture, so that will be a straight line, and we will heat it up in this case to 24 degrees. The total amount of moisture stays the same. The relative humidity obviously drops because we've heated up our air. And then we want to add a little bit more humidity just to make the air a little bit wetter. So that's our humidifier. You may spot here from 0.5 to 0.6, it's a vertical step up the line. So the temperature, dry bulb temperature stays the same. We're adding a little bit of moisture. And what we can then compare, we can compare the air supplied into the room at 0.6 to the air in the room at 0.3. 0.3 equals 0.7 is the same. So at that point, so if we compare those two, we can see how much of a difference there is in terms of the heat put in and how much difference there is in terms of the moisture put in per kilogram of flow of air. So if I flick to the next slide, you will see that. So it's the same condition, same chart, but what I've done here, I've added another table, so that shows me the values. The way I can work them out is I know my mass flow rate and I know my enthalpy at every point. So then I can just take difference in enthalpy. So for example, for the preheater, I take my flow rate and I multiply it by the enthalpy after, take away the enthalpy before, and that gives me my preheat. For the heater, the same thing, and so on. And then for the room load, I can also work out then if this is a stable condition where this cycle is working and the conditions in the room remain static, 18 and 45, I can work out therefore that the amount of moisture that I get from the room is 0.72 kilograms per second, and the heat load is 4.3 kilowatts. That's my load. So the way I work this out is by knowing the conditions at 0.6 and 0.3 and knowing the mass flow rate, multiply the enthalpies subtract one enthalpy from another, multiply by the mass flow rate. That gives me my power. So there you go. You can plot it like that. And you can work out exactly what's going on and say that's quite an accurate way of doing it using enthalpies rather than just assumptions for the dry air. Now let's look at a summer cycle. So in this case, slightly different situation. So we've got inside, we have 22 degrees, a relative humidity of 60, again, quite comfortable for summer conditions. Fresh air is coming in. Now, in this case, the fresh air outside is 28 degrees, so it's hot outside than it is inside. We need to be cooling down our supply air. Relative humidity of 42. Again, we'll be recirculating half of our air. We'll be mixing it together, cooling it down. Then we'll be reheating it. I'll explain why. And then we'll be supplying that into the room. We could potentially not reheat it, but then we will be supplying more cooling than we need. And if we didn't do it that way, then we wouldn't take enough moisture out. But let's have a look in psychrometrics. It'll make more sense. Okay, point 1 is over here. That's the outdoor air. So I can plot the outside temperature and relative humidity and work out other parameters from there. My return conditions are 22 and 60. That's 0.3. And once they're mixed together, that's my 0.4. So again, straight line, and I'm mixing 50-50, so it's halfway down the line. So that's my point where I'm mixing. Then that mixed air is going to go. Now, when it goes through the fan, by the way, technically, that would add some heat because some of the inefficiencies of the fan, they would add in. So I could show that as a sensible heating, but it's quite a small amount. So for simplicity on this graph, I'm ignoring it. But yeah, if you wanted to be really accurate, you could add that and you could have an extra stage where the fan adds a little bit of sensible heating. So no moisture added, but just increase the temperature. If you want, you could show that, but I'm going to skip that bit. And then I'm going to be cooling it. It will go through a cooling coil. Now, that's a very interesting process. The way I've shown it here is like that, but how do I know and why does it go like that? What would happen, you have to sort of think what's going on. Your air and moisture mixture is going through the cooling coils. And as it goes past the cooling coils, which are colder than the air itself, otherwise you wouldn't have the heat exchange, they're colder, the cooling liquid, that could be refrigerant in the DX coil or water inside the chilled water system, is absorbing heat out of the air. So the cooling coil is heating up, the air is cooling down. Now, generally speaking, what would happen is that you would have to be cooling like that directly, because until you get to the dew point, there will be no condensation coming out. So it all would be sensible cooling for a while until you get to the dew point, and then you can't just continue sensibly cooling because that's an impossibility. So instead, you would follow this curve down towards wherever point you want to, wherever you want to get to. And you would have both. You would have some reduction in temperature, and also you'll be squeezing moisture out of the air. Your absolute humidity will be reducing, and your relative humidity would remain on 100% line. That's what would happen in an ideal scenario, idealistic scenario. In reality, that's not quite what happens. Instead, as you can imagine, some air goes really close to the coil surface, and therefore it's in contact with a surface that's below its dew point, and it starts to condensate straight away. On the other air is slightly further away, and it doesn't condense. So on average, the whole air cools down, the whole air becomes slightly drier, but the way that it works is that you start squeezing some moisture out. But generally what you can often do, and another thing as well, is you'll practically never have 100% efficient condensation on the coils. So rather than having relative humidity of 100, that means that all the air is at a point where it's condensing, it's at the dew point. You will have a bit of a mixture. There will be some air that's next to the coil which will be condensing and which will be at the dew point, and then there'll be some that's further, it's mixed, and that will be off. And it will be off by, depends on the design of the coil, and there's a number of things that come into it, but let's say by about 3 to 5%. So rather than having our relative humidity of 100, you can draw a curve at about 95, relative humidity of 95, like that. And what we're saying is that you would cool down and then follow that curve down to whichever point you want. So that's basically what will be happening. So the cooling will be happening across that sort of angle like that to the point where we want to cool down. Now, we said that we would want to cool it down to, say, 7 degrees in this case, and the relative humidity will be 95. At that point, we would be moving on across, and then we'll be heating it up. So this bit here, that's the impact of the reheat. So that will be reheating it up to the point 6, which is where we will deliver it to the room. So now if we compare, you go from 6 to 3, you will see that the air is coming significantly lower enthalpy. Therefore, it will provide, be absorbing energy out of the room. It will provide a cooling effect. It's a lower temperature, 15 versus 22, and it has a lower moisture content. So that means that we're supplying drier air than what we're taking out. So we are constantly providing an element of drying to our room. And why is that probably good for us? Is that you can imagine this is a hot day, there are people in this room, people are sweating, their perspiration is adding to the moisture content in the room. If we were not to extract that moisture, it would go higher and higher, and the relative humidity would increase, and it will get very soggy and stodgy and stuffy in this room. So that's why we want to provide it. So that's basically what our cycle would look like, and you can work out various parameters from it. And again, if I go to the next slide, knowing my mass flow rates and knowing the enthalpy and absolute humidity at every point, it's very easy for me to work out what happens during each process. So for example, I can say how much cooling is provided by the cooling coil. I can work out how much heat is added back by the reheater, and then what my room load is in terms of my total heat in and my moisture in terms of grams. And the total heat I can also split into sensible heat and latent. So sensible is just adding heat directly, like a device with like your monitor, your computer, just adding temperature. Latent heat is the heat added in by some water evaporating, like for example sweat or breath from people, or if you're drying things on a radiator, or if you have a boiling kettle that pumps out vapor. So whatever is the source of it, that's the addition. And you can see that the ratio is quite big. We actually have quite a lot of cooling is not there to change the temperature of dry air. It's about the vapor that come in. So we'll talk about the ratio between sensible latent heat in a second, a little bit more, but let me just highlight something else that I wanted to show on this graph, is that why do we need the reheat in this case? So if we said, well, let's just cool down to this point, 0.5, and then supply the cold air straight into the room. Well, you could potentially, but the problem is you would be providing a lot more total cooling, so the temperature would start to drop. You will be freezing people in the room. You say, okay, well, in that case, let's just reduce the flow rate. So we're not providing so we're still providing at the same temperature maybe, but we reduce the flow rate. The problem in that case is that you say, well, that's fine. So in terms of the total cooling you provide, it will be adequate, but you will not be providing as dry air or as much dry air, so you will be not absorbing as much moisture from the air. Therefore, as I said before, the relative humidity would be climbing up and up and up in the room. So what we're achieving here is we're getting a perfect combination where we're providing just enough cooling and just enough drying to the room to keep it at the conditions that we need. And that's kind of the important thing. So that's where the sensible heat ratio comes in. That's the same graph as before, I just zoomed in on it. And what I've done is I've looked at the 2 points. 0.3 is the conditions in the room, and 0.6 are the supply conditions. And let's say we worked out that they actually match really well. They can correctly absorb the amount of sensible and latent heat. What I can do on the graph, I can draw a straight line through them. And what I can then do, I can also work out how much of my heating is latent, how much is latent heat, how much is sensible. So the way I would do it is, if I look between those 2 points, if I draw a line vertically down to do, 3 sides of the triangle like that. So the line that goes straight down, the difference between those 2 points is purely latent heat. So if I draw now lines onto my enthalpy chart, I can read out enthalpy at 0.3 versus enthalpy at this point here. And the difference between the two is the latent heat of the room. And what I can also do is I can go from this point to that 0.6, and again, check the enthalpy readings on both. And this is purely sensible heat in this case. So I'm just warming up from 6 to this point here. I'm just changing the dry bulb temperature. My absolute humidity stays the same, it's horizontal line. And then I check my enthalpies. And the gain here is my gain of the sensible heat. And then if I do a ratio of sensible heat to the total heat, that gives me a sensible heat ratio factor. What that gives me, it basically gives me the slope of this line. And what we're saying is that to maintain the correct conditions in this room, given the heat and the moisture load that there is in it, what we need to do is we need to supply air somewhere on that line. So if you're supplying higher up, for example, here, you would just need to supply more kilograms per second. If we're supplying over here, we'll be supplying less kilograms per second, less mass flow rate, less volumetric flow rate, but it will need to be coming in colder and drier, but it needs to be somewhere on that line. That's the important thing. And that's what you can work out and graphically show in a psychrometric. And then you can play around with your figures and decide how you will achieve it specifically in your situation. So that's kind of the useful bit about it. Now, of course, to do this calculation, what you have to be able to know is how much heat gain there is in the room and how much moisture there is gained in the room. And that's the tricky bit sometimes. So that's something that you would need to work out based on your specific challenge. That's the inputs that you need to have. But once you've got them, everything else you can work out using the psychrometric chart, because you fix the points and you calculate between them. Okay, just a few quick things before we wrap up and go to some questions. So one thing about the cooling coil sizing is what I described before. So theoretically, you would cool down like that and go down this curve. And for the cooling coil, you should have the curve and you should know the parameters that are there. Sometimes as well, when you're sizing it, there's 2 different things. There will be the cooling apparatus temperature, so that will be the temperature of the coil itself, and then there will be what's called off coil temperature, and that will be a little bit higher, because as we said before, if your coil itself is say 5 degrees C, the air that's coming off it will always be slightly higher, maybe 7 degrees C, and the relative humidity will not be 100 normally, it'll be something like 97, 95. So again, that's where your conditions will be a bit different. So when sizing, be a bit careful. It's not a huge mistake, but you will be off if you assume that you'll be sitting exactly at the temperature of the coil would be the temperature of your air coming off, because it wouldn't be as efficient as that. And another one to show is a issue with condensation sometimes. And again, that's kind of a problem where we did not provide for a reheat. We're just trying to solve the problem using cooling coil alone, and we're just looking at the total cooling capacity that we require. So the example here is where outside is warm and wet, 30 degrees C, relative humidity very high, 80%. And inside, we're trying to keep it at 20 degrees and relative humidity of 80. Now, what's going on in this case? This is our outside air, and this is our inside air. Sorry, so that's our inside air. No, sorry, it would be this one. Sorry, it's just the numbers in the wrong order. I apologize for that. Then we mix them together, that gets to the 3. And then we cool it down to 0.4, and then we will be supplying. Now, the supply air coming in and the air inside the room, what you will notice is that the supply air has higher moisture content in it, than what's already in the room. So that means that when we're supplying the air, we actually, yes, we're providing cooling, and yes, it's coming at a much lower temperature. So if you came and you put your hand to the air supply, you'd say, oh, it's much colder. Yeah, that's great. That's just cooling us down on this hot day. But what's also happening, it's adding more moisture. It will be adding more moisture into the room. And then, well, various things can happen, but quite often what happens is that moisture spreads around and finds somewhere and starts to condensate on the cooler surfaces. That could be the surfaces of the HVAC itself and so on. And they start to cool down on them. And that's where you start getting problems with mold and condensation, things like that, is because in sizing, people correctly address the overall cooling requirement in terms of the sensible heat, but they didn't think about the moisture removal. They've not accounted for it properly. What they should have done is cooled it further and then reheated slightly, and then that would have provided a better condition. That would be actually taking away the moisture as well as taking away the heat from the space, and that would be more of a correct way to do it. Okay, so just a quick summary of what we've covered before we go to some questions. So we looked at the psychrometric chart. We look at the various things that we have in it, the temperature, dry and wet bulb, and the difference between them, humidity, absolute humidity, and relative humidity. We looked at the enthalpy, which is the energy content, and how it changes with both change in absolute humidity and temperature. We looked at, well, density, we actually didn't spend a lot of time, but that's another property you can work out from the psychrometric chart. It's also fixed by it. And we looked at the dew point and the importance of it, and on both condensation that we want, like for example, when we're dehumidifying the air, but also condensation maybe we don't want when we have condensation in the corners of the rooms. And we looked at a couple of different processes and explained how you can map them easily with your inside air conditions, outside air conditions, mixed conditions, cooling, heating, dehumidification. You can work out your cycles, graphically represent them, and better understand the energy balances inside your HVAC systems. So I hope that this brief overview was useful to yourself and you have a clearer view of how psychrometric charts and calculations can help you in your design. And that's all I wanted to cover today. And I think now we can go over to the questions. So Rob, I don't know if you've picked up any questions in the chat.
I think, Alex, you've done such a good job that we don't have any questions. You've explained everything perfectly well. I don't know if anyone wants to add any questions into the chat box now that we've finished, or if you want to add any bonus material, bonus content, if you want to go over anything else, Alex, you think might be of use.
Yeah.
Before you do, as we mentioned at the start, here's the details of our HVAC design course. Please feel free to go onto the website, look at that, or use the QR code. And I think, Rob, you've put the web address in the chat as well. So I think we take it from there, Alex. I think we have no questions at the moment.
Okay, well, that's fine. Hopefully it's because everything was clear. Maybe it's because people are still digesting what I said. I had to rush a little bit towards the end, so I think if we have just about 5 minutes, I maybe just do a slight clarification. Thank you. Excellent. So yeah, I say just a bit of clarification on what happens here. I think this is the one that I want to also highlight. What's going on. So the brown line, similar to the previous chart, that is our sensible heat ratio for the room. So that kind of shows the gradient between the amount of cooling versus the amount of drying that we want to provide. So you can work it out based on whatever inputs you have, and you can plot it on your chart. And then what happens is if it goes across and eventually comes off the chart completely, then ideally this is the point to which you want to cool down your air. And then when you supply the air, you can supply it right off the coil and into the room, and it will go up on this curve back to the point. So we don't need any reheat in this condition. However, if you look at this situation, see this line, because there's so much dehumidification required, if you continue straight, you're never going to hit a point where you can use straight off the coil conditions. It's always going to be either not dry enough or too cold. So that's why what we need to do is overshoot and then bring it back to meet the line. So I think that's important as well, is if you look at the geometry of your line for the condition of the supply air that you desire, if it's like in this case, then you would want to use a reheat. And if it's coming off, then you can just use an off coil condition directly, as long as you pick it correctly. Okay, I think there's a question there from Hassan. Does the debris in the air play any role in our calculations? Generally speaking, no. I would only say that if you have extreme amount, so if you have a huge amount of say solid particles like sand or something like that, and then you're heating up or cooling down, then you maybe want to start thinking about what's the change by mass. But that would be a lot easier to allow for, to be honest, because if you were carrying a very dusty sandy air, then you would know how much it is and it would stay permanent, because unlike vapor, it's not going to be changing phase. So again, you can just work out that for every kilogram of air, you're carrying 10 grams of sand, and sand has a following heat capacity, and you can add it as a mixture. But generally speaking, practically never do you need to worry about this. And then I think there was a question from John. For evaporative cooling, which line do we follow diagonally up to the left? So for evaporative cooling, yes, it's this one here. I'll just quickly click back to it. Yeah, so evaporative cooling is this one's basically it's a diabatic line. So that's what tends to happen. That as the water evaporates, it absorbs the heat. So it's a very efficient way of cooling. The only problem with it is that at the end of it, you have a very, very saturated air, which is full of moisture. But if that's not an issue to you, that's a very good way of cooling.
There's also one further up from, if I can find it.
I can see one from Jack Owens.
Yeah.
So he says, are there any recommendations for dry room assessment, for example, for Lion production facilities, -40 dew point, how occupancy affects the latent heat gains? Yes, so I guess you could. Let me just flick to a chart with various parameters on it. So, by the way, -40 dew point, that's something I didn't cover, but the idea is it will be off this chart, but you can get a chart that covers it. It's no problem. But if we say a dew point of -5, it means that's condition here. So that's the absolute amount of moisture that would be equivalent to -5 dew point. So -40 would be very, very, very low absolute amount of heating. In that case, what we would do, so yes, people in the room definitely will add to the problem, because people almost always add perspiration, and you would need to account for that. And there's two ways. You can either work out how many grams per person of moisture they are pumping out through their perspiration, or you could do it as the latent heat versus sensible heat ratios, and that can be done. There are values. So if you look in the SIPS reference data, or if you look in ASHRAE reference data, they do provide heat values per person, and they will typically give you also different values depending what they're doing. So for example, are they working out like in the gym, or are they sitting quietly in a concert? There will be a different amount of both. And as you can expect, when they're working harder, the amount of sensible heat actually changes little, because their body temperature doesn't really go above 36.6 that much, but the amount of sweating and perspiration they give out increases dramatically. The other thing to consider is how they're dressed. So in a clean room, if they're wearing sort of paper overalls, most of the perspiration would stay within it. So then you can probably ignore a lot of it. It will be mostly the face that will be coming from. But if they're quite scantily dressed, or dressed in something that allows the vapor to come through, in fact, it could be completely covered, but if it's cotton or something that easily lets the vapor through, then yeah, they will add quite significantly, and that needs to be taken into account. And then you can work out how much they're adding, and you need to make sure that you supplying enough dry air to absorb it and take it away without changing the conditions in the room.
Got questions from Alan and Stephen as well now, Alex.
Yeah, so I'm just having a look. So earth tubes are used in some countries. So the idea is you take cold air from outside, maybe -20, put it through the ground. That's maybe at -2 degrees, I would assume, or something like that, because it doesn't get that cold, especially if it's deep down. And then you bring it back in, and it says when cooling. Oh, sorry, for cooling. So no, sorry, so not for heating. Preheating. Yeah, okay. When cooling, does the air reach its dew point? Yes, so it probably will. Yeah, I would expect that it very likely can. Again, you could plot it on the chart. So if outside is, for example, if you take a point and outside is, for example, 30 degrees and the relative humidity is quite high, then when you're cooling it, depending on the temperature of the earth itself, so let's say the earth is at 20 degrees, then yeah, if you come across, you'll see that you would start cooling down before you get to the temperature. So I would expect there'll be an amount of condensation happening on the surface, on the inside surface of that pipe. And then you would need to have some sort of condensation pods and somewhere for this condensate to flood away from. Otherwise, you'll fill your pipe with water eventually. So yes, that's something you would have to take into account, depending on the temperature of the pipe or on the earth around it, I would expect. When did you get it? Where did you get the chart for typical London external temperature from? Is there somewhere online? Right. So there's various places you can get them. I will quickly show you exactly where I got the one that I have. Just 1 second. I just need to get the website up. So there's this website here. I'll put it in the chat for those who are interested. I have nothing to do with the creator of it. I just use this tool online. And also I would say if you're using it, please you verify that all the data is correct. I've never found any issues, but equally say I've not verified it myself. But what you can do on a chart like this, why I like it, is you can do data mapping where we can load up a station. So for example, London, and that shows you, or I could load up another one, but then you can find a different weather station for the location that you're interested in. If you go here, you can find data, but similar data can be found from places like Met Office or the American what's it called, National Oceanographic Association or something like that. If you Google for that, they have loads of weather data, and once you have the data, you can then input it into various software in various ways. So you can find different locations and you can pick them off, and then you can include them into the software. So that's where I came up with mine. Again, it's quite good when you're trying to come up with conditions for your specific location. That is quite useful. Okay.
Brilliant, Alex. I think that's taken us to past, and thank you for those who answered the questions. That's fantastic. Thank you, Alex, for an exceptional webinar, one of our best. I think that was really good. And thank you for those who attended. Excellent, and hope to see you at our next webinar.
Yeah, thanks a lot. And thanks to Rob and Rob, my two colleagues, for organizing and helping run this today. That was very good. I apologize a bit about the sun has moved and I realized I'm really much in the shade at the moment, but hopefully you saw the slides clearly and the explanations were clear enough. So thanks a lot. There's many more webinars from IMechE, L&D. Please have a look online and hopefully see you later, either one of our courses or on one of those webinars or other events.